a key value store. So design a key store. So we'll start with the requirements. Start with functional requirements. It's quite simple. We want to get data, right? So retrieve the data from the store. And the second one will be stored data. So we want to put the key value pair to the store for later access. The third part, so for the functional requirements, could be for the value, could be any type. Then the non-functional requirements, scalability. So we are talking about very large amount of data, definitely need to scale. Availability. So you want the system to be high available, more than like 3 or 4 nights. 3 or 4 nights. We want the system to be low latency or like high performance. Since like for Kiwi Store, they were actually mostly used for cache, so in a distributed system. So high performance, low latency. We also want to talk about the fault tolerance, which means the system should still perform if some nodes or some components were in error, or either a timeout or network issue. We still have other, or the many of the system will still function well. That also the reliability. So no single point of failure. Actually, those we can say no single point of failure be part of the reliability. And then for fault tolerance will be like even like network issue, hardware issue, or even outage, data center outage. The system should still function well, maybe in a certain degradation. That's the high level requirements, including functional, non-functional. Here we can also talk about a little bit on the API design. So we do not need to talk about data storage. We don't have like example here. For example, like what type of data or what amount data we are talking about, but just keep in mind this may be a more like generic KB store, and we want to store as much data as possible. For example, terabyte data, a PB, or even more than that. So then the definitely like scale, we'll keep that in mind when we design the KB store. We can quickly talk about the API. Actually, the API could be the high-level design. So let's just get into the high-level. Sorry, not the high-level design. For this case, then we do not need like 10 minutes just talk about the requirements, since the requirements is quite clear or straightforward. So for a high-level design, let's talk about the API. Very simple, just get, and then the return will be the value. So the value could be object, could be a string, could be a different type, map or etc. And then we have the put, it will be key and value. So the put will be just store the key value pair into the data, into the key store. That's the API. And now let's start to draw the high-level design. we'll start with the system diagram. So we have the client here. We may have a load balancer. Oh, so we may have load balancer in between, and then we will have the coordinator here. Oh, coordinator. So the request comes in, and for the load balancer, now we know who will be the coordinator. And actually, it will be a ring here. Oh, I don't know how to draw this in as a ring. I just did this. Okay, so this is the coordinator, and we will have different node. So here we have another node. Let's say node B or node A. The coordinator could be node A. Then we have node B. We have a different node here. Could be C. And different one here. Could be D, etc. So we have a different node on the, it's a ring. We can talk about that later. So for the read, we will try to, it also depend on consistent model, like strong consistency or eventual consistency, like what consistency level we are talking about. So usually may just load data from the coordinator and maybe one or maybe just from the coordinator, or it may be from coordinator and another node, depending on like how many replicas we have. We can talk about that later. That's like the read. So this one and this one is optional from different nodes. That's read. And then we can copy this. Oh. Interesting. What if I just move? No, it will not work. Okay. So seems like we cannot copy this. Control C. Oh yeah, we can. That's great. So let's do it right. So that's a read. Oh, let's change this to this way. So that means read. And then for write, the client will write the data, like we'll call the put key value pair, and we'll write the data to node A. And also depend on the consistent model, like do we need strong consistency in writing? If yes, we will write maybe to all the replicas. So we will write to A, and then we'll write to B, and then we'll write to C. Like if we have 3 copies of the data, we have 2 more, like B and C will be the replica of the data. And we write like clockwise, like this, like this, yeah. So we firstly found B, and then we write to another node C. And if B and C, if they are virtual node, we'll try to find a different physical node to write the data to. So that's like the write flow. That's like the very high level. And for each node, we want to also draw like how we write and how we read. So for each node, we have the client here. We'll skip the load balance. So just write the data to the node. Oh, let's just draw the node. That's like the node we want to write the data to. So in the node, we'll have the cache, right? So we'll start to write to there will be commit log. So it'll write to the commit log. It'll write to the cache. And then if the cache is full, we'll try to write the data to the SST table, which are on the disk. Yeah, that's like the write on node. And then for the read, we'll definitely try to read from the cache here, right? So read from the node, we'll try to read from the cache, and there could be cache hit, or if we cannot find in the cache, then we need to read from the SST table, right, to get the data. And how to quickly get the data from the SST table, we can use the Bloom filter here. To quickly get the data and then load data to the client. Then we can also put the data into the cache. Like because it also depends on how the cache like what the eviction for the policy for the cache. If LRU like least recently unit, so we can use that. So that's the read write for each node. That's very high level. We will talk with the interviewer, and we will quickly go through all the use case, right? And then now let's go to the detailed design. So we got buy-in from the interviewer, and now we start to talk about each component. We want to talk about the edge case, dive deep. So let's start with the sharding. The if you see here, the data we are writing or we are loading from different node, right? That's like the replica. Actually, this is more on the replica, not on the sharding. So for the sharding is like, what if we cannot store the data in a single host? We can try vertical sharding, but as the like more data growing, we just cannot store the data in a single pod. So there'll be like sharding, and how to shard. There'll be like two main issues here. The first one will be the hotspot. If we didn't do the hashing well, or even like there'll be like hotspot, and then for the keys, if we change, add, or remove nodes, we may need to rehash a lot of keys. It depends on the hashing algorithm, like how we do that, but here we will go with the consistent hashing algorithms. You can check my previous video on that. That would like fix both of the issues. The second topic, we want to talk about the replica. So, or replication. So you want to have more than one copies of the data. It's like the redundancy. We have extra data for like the reliability. There's no single point of failure. We can support fault tolerance for this. So for the replication, there are a couple of ways to achieve this. One is the primary, secondary mechanism. So like we have one node for primary, we have maybe like 2 or 3 nodes for secondary, and you can read or write to the primary node, and you can only do the read from the secondary node. So it's like it works pretty well for read heavy, but for the write, it may not work well, and we have a single point of failure for the primary node. So for that case, we may go with like peer-to-peer model here. So for peer-to-peer means like we have a ring of the node, and for each node here, node A, node B, node C, node D, one of them will be coordinator. And each node we will rotate the coordinator role. So each node can read and write data. So here the challenge is how to make the data sync, right? How to with the peer-to-peer, how to make sure like the consistency. So there are different consistency models here. We may want to go with like strong consistency, or like eventual consistency. So for strong consistency, here we have read. Every time we read, we'll read R copies of the data, and every time we write, we'll write W copies of the data. So as long as R plus write greater than N number of the node, so we can achieve like strong consistency. However, for strong consistency, we may sacrifice the availability. For example, when we read, we need to read more than one copy probably, and then we will wait for the slowest node to return the copy of the data. So actually that's the theory CAP, and with partition P will always be there, so we have to choose either AP or CP. So here if we choose CP, C means like consistency, then we cannot achieve the availability, right? So that's like the theory CAP, cap. So for eventual consistency, if we want to go with eventual consistency, that means eventually we'll get the data consistent, but for some time we may get inconsistent data. That's okay, like okay for inconsistent read or write. What does that mean? That means like at the same time in our system, for some key we may have different values, and then how that mean? Yes, eventually they will be consistent. So how to fix that? We will use the versioning here and the vector clock to fix that. Long story short, you can read a lot of books on that. The versioning will be like every time we write a data, like for example, using node 1, we write a 1. And the next time, if we still write the data using node 1, we'll increase the version to 2. And if the next time we write we're using a different node, we write the data, so it'll be N1, 2, Okay, first write, second write, the second version, third write, maybe a different node. We'll have different node here and 2 and 3, and then we'll have the data, we'll have the the context of the data before this version, for example in 1 2, so we have that. Okay, so then if at the third write we have another write on 3, so we have this data, right? And 1 2, now if a client load the data about the third write, so it will realize, okay, there's data inconsistency here and we need to fix that. So then we have these are the vector clock. You can see the history of the data, and then the client, the fourth write will make it right. So for example, the first write will do the reconciliation and get the data right. So for example, N4 and 4, or actually 5. So there are like 2 versions, and then we'll get to like N2 3 and 3 3 and 1 2. So you can see all the history of the data. And then now the N4 5 will be the latest, the correct one, and eventually it will be consistent across the whole the whole like system. That's the versioning and the vector clock. That's like how we fix the inconsistency. Let's also talk about the failure mode. So now we have the system, we have sharding, we have replica, we have read and write, and we choose a model like strong consistency or not. We do have like with multiple nodes, we definitely have failures, right? We have different failure model. Let's talk about the failures. So firstly, how to identify the failures? We can use gossip protocol, which means like each node will randomly talk to other node, sync on the data, and make sure they're on the same, they're in sync, and they have the heartbeat, and they keep like talking to each other. And if, for example, if a heartbeat from like N1, N2, let's say, is missing, missing. Okay, so the heartbeat from N2 is missing, and then for N1, if N1 had talked to N2 before, then N1 will try to ask all other nodes, or not all other nodes, ask random nodes on N2's status. And if all confirmed, N2 heartbeat missing, then N2 is like offline or something wrong, right? So that's like the gossip protocol. And then we may have like temporary, the node maybe like temporary failure. So here we'll use like hinted handoff. Every read or write to N2 will move to N3, and if N2 come online, we'll move back to N2. That's like temporary. But if permanently failure, for example, N2 just hardware issue and we just lost all the data, so we need to sync or replicate. We need to firstly we need to start a new node, and then we will sync all the data. It was on N2 and now they were gone, right? So we need to sync all the data to the N2. So here we'll use a Merkle tree to do that for quick hashing check and data sync. So you can read some blog or books on the Merkle tree. The high level idea here is if the hashing value of tree node is the same, then no need to sync. No need to sync. They're good, right? So like they're the same. So you can use that the Merkle tree for that. So that's like the failure, different failure, temp, permanent failure, hardware issue, etc. Yeah, that's the key value store. And let me see what we missed here. Maybe I think we covered most of it. Hope you enjoyed the video. And I mean, a lot of these design are from like DynamoDB, and we just use DynamoDB as the example here. Oh, let's quickly go through the requirements. Get function requirement, get, store, or put. So get and put. So let's say we have that any type. So it's a generic type for the value. Non-functional scalability, we can auto scale, we can add more node, we use consistent hashing to like dynamically add a virtual node, etc. Availability, so here if we use eventual consistency, we will have a very high, where is the CAP theory, CAP theory. So here, if we really want to focus on availability, we can prefer AP instead of CP. So we can just read and write to one node, and then wait for the async copy for the eventual consistency. High performance, yes, we can get a high performance of that. Fault tolerance, yes, we have the different copies. We can add more copy. Reliability, no single point of failure. I think that's it. Thank you.